All right, hello. Today we're going to approach problem 1857, largest color value in a directed graph. Um, Full disclosure, this is not the first time that I've approached this problem. I solved this problem a few minutes ago, but due to some technical difficulties, the recording was corrupted. So I'm just going to go through this problem quickly, um, and hopefully there's some information that I can relate to you that's helpful. Okay, so let's just get ahead and get started. 1857, largest color value in directed graph. Okay, so there's a directed graph of n colored nodes and m edges. Okay, n nodes, m edges. The nodes are numbered from 0 to n minus 1. Okay, you're given a string colors where colors I is a lowercase letter representing the color of the ith node in this graph, 0 index. Okay, so there's for each node, there's a corresponding color, and that color can be found by indexing into this colors array. You're also given a two-dimensional array edges, where edges indicates that there's a directed edge from node A to B. Okay, so you're given each edge, so you're probably going to need to do some sort of conversion to get it into a graph form that's easier to manage. Okay, there's a valid path in the sequence of nodes. Okay, so there's a path in this graph. The color value of a path, so just a path in a graph, like a normal directed graph path, where the color value of this path is the number of nodes that are colored the most frequently occurring the most frequently occurring color along that path. So every path, has a sequence of nodes. Each of those nodes has corresponding colors. So which color occurs the most in that path? Okay. Return the largest color value of any valid path of the given graph, or -1 if the graph contains a cycle. Okay. So first thing we have to do before we even think of the rest of the problem is when you look at things like this problem where we have edges given like this, almost always what you do is convert edges into adjacency list graph G. So all you basically do there, and I'll do that really quickly, is you just say, well, we're gonna make this graph G where every node is represented by a list and its neighbors are members of that list. So for blank in range length of colors. And so we have this graph G, and then for U, V, and edges, so for each edge with the starting vertex U and the ending vertex V, that means that G can go to V, so we say G of U append V. So that gets our form into a graph. So, even if you can't solve the rest of this problem, at least you can do something, because that's a portion of the problem. Now we're trying to find the color value that occurs the most. So we're going to do some traversal of this graph. Another note is if there's a cycle within this graph, we need to return -1. Okay. Well, what's the best way to traverse this graph and to find a cycle and to ensure that we don't do any extra calculations? And to me, that sounds like a perfect opportunity to do topological sort, right? Or a topological traversal, I guess, of this system, right? Where if we find a cycle, we return -1, we terminate. Otherwise, we keep traveling through and reuse information that we've already found. So we'll start with just before we continue the problem, I'll just write out a simple approach to topological sort that I've devised that would find if a cycle existed, and then we'll continue from there. So the first thing you do is you create this array visited. Which is of size, length of colors. And then for each vertex, you're going to check if that vertex has already been explored. So if that for each vertex U, we're just going to say if that vertex at U equals 2, that means that this vertex has been explored already, so we don't need to re-explore it. If that vertex at U equals 1, that means that the vertex is currently on the stack, and I've already explored his vertices, so that means there's a cycle. The idea, of course, is, now I'm not going to spend too much time going into exactly how topological sort finds cycles, but every time something is put, so let's say we've traversed these nodes so far, and there's a path like this, if there's no cycle, every time I put a node as green, that means that it's been put onto the stack. So imagine we explore this next node that's blue. If this node that's blue has any path back to a node that's green, that means that there's a cycle in this graph, essentially, right? So if I have a neighbor that's currently on the stack, that means that I have a path back to something that's calling me and waiting for me to finish, right? Because when I put something on the stack, that means that this thing is waiting to be finished. So if it's still waiting to be finished, that means that it's called me. And if I can get back to it, well, it's waiting for me, and now I'm waiting for it. That can only occur if it's waiting for me, so it has a path to me, and now I'm going to be waiting for it, so I have a path back to it. Therefore, there's a cycle. But we don't need to go too far into that. I'm guessing that if you're doing a hard problem, you probably understand how top sort works, at least fundamentally. So that's when you return false. If v equals 2, that pretty much means that it's not waiting for me anymore. I just don't need to traverse it again because it's already finished every operation. If that thing has already been processed fully. And that can happen if you start at a node after a previous. So if you start at node 2 into top sort, right, there's no cycle. But then if you go to node 0 and get back to 2, you don't want to process it again. So it's just saving you some time. Okay. So now this idea of waiting. So waiting means it's on, it equals 1. After it's finished, it equals 2, which means that it's finished. And then you look at each neighbor in the graph at you. So for each neighbor, you do, so if not, DFS of V, so if any of my neighbors return the fact that something's on the stack, that means that there's a cycle, so we return false. So that's basic top sort for finding if a cycle exists. But we need to adjust this to manage the fact that we are dealing with this idea of finding max colors. So let's look at this example here on our paper. So we have a top sort idea for traversal, and we have the top sort set up such that we can find a cycle. Let's just go ahead and finish that actually. So you look at each node in range length of colors, right? Because that's how many nodes there are, colors. And we're going to say if not DFS of U, right? So if any node it returns that there's a cycle, we return -1. So this is the perfect code for finding if there's a cycle in a graph, right? You could just memorize this or intuitively try to understand this so well that you can always determine this code or whatever. But this is the perfect code for finding a cycle in a graph, in my personal opinion. Okay, so now let's look at this color situation. So let's say we had the case of this. So if it's red, that means that it's colored red. If it's blue, then it's colored blue, etc., etc. And this one, it's not a color that I have as a base, but it's fine. Okay, purple. Okay, and then we have these paths between nodes. All right, now let's say that for whatever reason, the top sort algorithm started here. So it started exploring this node over here. We'd want to collect the current colors that we've seen thus far, right? Because we want to find the path that has the maximum number of colors. So if we're looking at all paths, right, we kind of want to start looking at sinks before we look at sources, right? So this path is a combination of this path. It's kind of confusing. I'm trying to think of the best way to describe this. Right, like this path here has red once. And then when it returns, this path, since this path can go to a sink, right, you might as well include that path because we want the maximum path, right? There's never going to be a situation where like our path is just these two nodes. I guess that's the point I'm trying to get at, right? Because including more nodes, you're trying to get the maximum length path, right? Because including more nodes is only, not maximum length, but your path is always going to include a sink because it can only get better, right? Meaning that you can only get more color values by traversing more nodes. So there's no reason to not traverse more nodes if you have at least one, right? If you have one child node that you can get to, you're going to want to include it in your solution because it's going to only add an extra color, right? There's not going to be any penalty. So there's never going to be a situation like this, right? There's always going to be some path that goes to an edge, right? So I guess that's the general idea that I'm trying to get to here. So what you want to do then is kind of like a dynamic programming idea, right? You want to look at the last node, a node that's a sink, and then collect its values and start propagating them backwards, right? So this one has red 1, so it's going to push that information back here. And this one will say, okay, well, I have a neighbor that has red 1 and blue 1, and it's going to push that information back here, right? Now remember, I said we started here, so this one will stop and say, okay, I have red 2 and blue 1, right? Now we can maybe look at each of these nodes, but since they've already been explored, they're kind of finished. So all of these will have v at this value equal 2, 2, 2. All these things will have value 2. So the next time our DFS asks a question here, since the value is 2, we don't need to keep traversing. We can just return the information that we've already pre-calculated for this one to make a determination about what to do. Now, here is the only case where a node has multiple children. So how do we handle the fact that this node or this vertice has multiple children, because that means there's multiple paths, right? Because a path can't like cross here and then go back and then go back here, right? Since there's no cycles. So he either has to choose, let's delete a lot of this red. So when this node gets to where it's at, this first red node at the very left, right? This node has to choose, am I going to take the maximum from this path or the maximum from this path? Well, I guess the trick in this question is, since we're only looking at one color, right? I could say, well, the color, right, like the color at this node, so I'll just call this node X. The color at X for some color like red is the max of the colors of a neighbor at red for each neighbor of X, right? And then if it has the color, if X is red, then you would add 1 to this, if that makes sense. So the color of red for here is like, well, what's the max of red for this whole system? And what's the max of red for this whole system? Right? If I have any single node and it has multiple paths, right? When it passes information back, when there's some parent node that calls it, and this blue node passes information back, it wants to pass information for its maxes for each of the colors, right? When this node asks, hey, I need, what's the best red path? What's the best blue path? What's the best green path? This blue node can respond and say, well, my best blue path is down here, and my best red path is down here, and my best orange path is down here, right? They don't necessarily the same paths, right? So as long as you just collect information for the best colors, what the best path sum is for each color, then you can determine what the most frequent color is, right? Because the issue here is you can't just sum them, because we can only take one pathway in the system, right? So I can't just sum them all together and return that, but I can give them information as a distinct path for each color. And then this person can decide if they have additional paths, what to return. So that's probably as best as I can describe it. Probably later it'll hit me and I'll be like, oh, there's a way better way of describing it. But that's the general idea of this problem. And with that, I'm going to start coding, and hopefully that maybe will help out a little bit and make this make more sense. So essentially each node, we're going to call it D. So it's kind of like, it is a dynamic programming problem. Each node will have its own set of colors, right? And how many colors are there? There's 26 in range length of colors, okay? Now, to get the color associated with the letter, we're going to say the order of the colors of U, so the minus order of A, right? So that'll give you the offset for the color, plus equals 1. Now, after you've done DFS on your child, then it's been properly filled with its corresponding color values. So you'd say for each color in range 26, so for each color, we'd say colors of U at that color equals the max of itself, because right, meaning that why is it max with itself? Well, maybe my previous child has more, has a higher frequency of that color along its path than my subsequent child. See? Or maybe it doesn't, and the subsequent child has a higher value for C. Okay? And I think that's it. So we return the max of the color for color in D. Sorry, I was thinking about something else. Previous solution I used. Okay. Previous solution I wrote like 5 minutes ago. Okay. Int object is not iterable, so what did I do wrong here? Oh, because we're talking about U here. Yeah, see, I did it a few minutes ago. All right, cool. So that looks good to me. So let's walk through this just a little bit more since we have some time. I'm looking at the clock like I'm in college tutoring. We have all the time in the world. The basic idea here is, let's see if I can make a really extreme example. So let's say we had a parent node, a red parent node, a blue child node, and then it had like extreme paths like this. All right. Maybe this will make the idea more clear. So when this node returns, right, what is its best path for a color? Well, its best path for a color, just for a single color, would be, let's say there's an additional one here. Right, its best path for a single color would be red, right? So you might say, well, the best path here is red because red is the most frequent thing occurring here. So maybe I should return the red's value, right? Because there's a red here. But imagine there was a system of green behind this node. There was 11 greens. Imagine there was, why did I do so many? Okay. Imagine there were more greens back here. So when you return from this path, you may be, if you only had the information that was here so far, you may be inclined to say, well, red is what I'm seeing the most of, so I'll return this red path. But it's not but the truth is that green actually has the largest frequency, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, versus 1, 2, 3, 4, 5, 6, right? So green is far more frequent. So you don't want to just return the red information because something before the node you're exploring might have a greater color of a different path. So you need to return information about each color, right? Because again, this idea is you can't sum everything up, but you can say, well, my maximum red path is this, right? And it has this value. And my maximum green path is here, and my maximum yellow path is here, right? Because what you're trying to do is maximize the one color's frequency. So you just need to find the path that maximizes one color's frequency, right? The frequency of one color and one color alone. So by counting for each color in that associated path, you can find the path that has the most of the color that occurs the most, right? And they're kind of equivalent things, what I'm saying here. So I hope that idea makes a little bit of sense, right? I'm trying to think of it in terms of something that's more more realistic. Like you could think of this problem as like software engineers, like different colors are different people that work under you, right? And you could say, okay, well, I have, 10 software engineers working under me, and I have 12. You're not even finding a path, right? You're just saying, how many of each thing do I have under me, right? That's kind of how you're rephrasing this problem. It's like, how many of each color comes after me? Like my wife is calling me. That's funny. How many of each color occurs? Send it right to voicemail. How many of each color occurs under me, right? After me in this node. And then I return that information. And when you get to the source, you say, well, how many of each color occur in one single path? And that's all I can give you because I'm distracted by my wife. You guys want to say hello? Hello?
What are you doing?
Leetcode, what are you doing?
I'm at
In and out and about.